Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 3.2.1, which is Constant Ratios in Right Triangles. And so this is problem 3-68. And basically, they're giving us this diagram here. They're telling us that we have a line, and it creates a slope triangle of 1/5. And whenever you have this slope triangle of 1/5, and we have to give them kind of the benefit of the doubt here, they took a protractor and measured it. The angle of elevation from the ground up to the line is 11 degrees. So when they talk about 11 degrees, they're talking about this angle here that I'm highlighting in purple right here. And they're telling me that that's 11 degrees wide. And so what we're going to learn today is we're going to learn how these angle measures are affected by their slope. And so in part A, they're asking us to draw 3 new slope triangles on the line. Each one should be a different size. We're going to label the information with as much information as we can, and then such as vertical and horizontal length and angle measures. And so let's go and do the first one in blue. And I'll go and just dot him right here. And this one was 5 long, but what I'll do is I'll go ahead and go up to about right here. And I'll go and connect that as a slope triangle right here. And so this slope triangle here looks like it's 1, 2, 3 long, and this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and lo and behold, 15. Now, for some of us who didn't see that coming, I understand, but if you did see it coming, that should have been somewhat predictable because the top length is lengthened by 3, right? I multiplied the side length by 3, which means the 5 had to get multiplied by 3 in order for this shape to maintain similarity. Now, if you were to take out a protractor and measure this angle again, you would actually get 11 degrees just the same as you did before. Let's go and draw another another triangle on here. So maybe I'll go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know, like maybe out to here. And I know I'm going kind of off the grid here. Maybe that first triangle was a little too large, but if I made the bottom length 10, I think we could very reasonably guess that the vertical length would be 2. Because again, I'm just multiplying the sides by 2. My scale factor is 2 on that one, and again, 11 degrees wide. That shouldn't be very, very surprising. Now, explain why all of the slope triangles on the line must be similar. I'm going to explain that by saying we multiplied the base and the height. We multiply the base and height by the same scale factor, so they must be similar. And therefore the slope ratios must therefore be the same. On top of that, the first answer here in part B, another reason why that's true is they are also similar due to our good old buddy angle, right? They are also similar due to a similarity. I'm going to put that right here. And again, what are the 2 angles that we're talking about? Well, they all have the 11-degree angle in common, and they all have this 90-degree angle in common as well. So angle similarity and all that stuff. And now it says, confirm your conclusion by writing the slope ratio for each triangle as a fraction, such as delta y over delta x. Well, each triangle here, the delta y over delta x is 1/5 for the first triangle. Then it's 3 over 15, which reduces to 1/5. And this is 2 over 10, which reduces to 1/5 also. So all of these ratios here, they all, whether it's 1/5 or 3 over 15 or 2 over 10, they all simplify into 0.2. And that is the last question of this section right here. So again, we're going to start to realize how this affects constant ratios in right triangles. Give me a second. I'll be back with the next problem. All right, coming back to 3-69 here, it says Tara thinks she sees a pattern in these slope triangles and decides to investigate whether or not the pattern remains true. So in part A, I'll go and switch colors here to white. In part A, she asks, what if I draw a slope triangle on this line with a delta y of 6? Well, let's take a look at our original slope triangle. Remember, our original triangle here had a delta x of 5 and a delta y of 1. Again, this is 11 degrees right here. And she says, what if there's a slope triangle with a delta y of 6? Well, what would be the delta x of the triangle? Well, again, we just found out in the last problem that these are all similar triangles, right? So if I multiply the 1 by 6, I have to multiply the 5 by 6 to get 30. So that means that delta x has to be 30 on similar triangles because the scale factor of this particular triangle is 6. And then if she says, what if delta y is, in part B, in part B, what if delta x is 40? So let's go and compare that back to our base triangle right here. If the delta x is equal to 40, and again, if we're still dealing with this 11 degree arc right here, or 11 degree change of angle, that means that this 5 was multiplied by 8 to become 40, which means the 1 would have to get multiplied by 8 for this to become 8 as well. So again, explaining the reasoning, we would explain similar triangles would be all increased or decreased in size by the same scale factor. So let's go and type that in. Similar triangles are increased or decreased in size by the same scale factor. And that is how we were able to figure out these sides quickly. So in this case, the scale factor was 8. And then Tara wonders, what if I draw the slope triangle on a different line? Can I still use the same ratio to calculate delta x or delta y? This time you're supposed to discuss with your team. We won't get into that right now. We'll just move on to 3-70. It's more supposed to be an open-ended discussion rather than something that is meant to teach you anything. I'll be back with the next question. And we're back in 3-70. It says in part C of problem 3-69, Tara asks, what if I draw my triangle on a different line? With your team, investigate what happens to the slope ratio and the slope angle when the line is different and use the grids. Okay, so let's go and graph Tara's line here. So it's going to be up 2 to the right by 5. So up 1, 2 to the right by 1, 2, 3, 4, 5. Up 1, 2 to the right by 1, 2, 3, 4, 5 again. And we're supposed to connect here. Connect those 3 dots like that. And so what does the slope angle appear to be? At this point, you're supposed to collect protractors and measure. What you'll find is this thing ends up being about 22 degrees, which should hopefully make a little bit of sense, right? Because your original slope was 1/5 x. With your slope being 2/5 x, double the rise but the same run, you should end up with an angle that's double the measure. And so, yeah, that seems to support the conclusion, okay, of 3-69. Sure. Okay, let's take a look at part B. I'll be back with the graph of that one. And in part B, it says you're going to create angle QPR so that it measures 18 degrees. Now, again, you're supposed to have a protractor for this one. And so, honestly, the work is going to be pretty much, I'm going to give it to you here because, I can't really do a protractor on this program here. So we have to draw the protractor so that point P is at the vertex, and then find 18 degrees and label the new point R. We have to draw a ray, and what is the approximate slope? You're supposed to just be discovering this. It's basically, if you do 18 degrees, it's basically a slope of 1/3, up 1 to the right by 1, 2, 3, up 1 to the right by 1, 2, 3. And again, how did I get this so fast? Well, it's because, I'm not going to lie, I looked at the answer at what it was supposed to be, but you're supposed to use a protractor to figure that out. So that is 18 degrees. No, not 18%, 18 degrees. And again, the delta y over delta x of 18 degrees is approximately 1/3. Again, you're supposed to kind of work that through on your groups as well. And then the last one is going to be part C. Give me a second. Let me get the graph paper, and then we'll do this one. And in part C, they give you the equation y equals x plus 4. Now, interestingly enough, 1, 2, 3, 4 here, and has a slope of 1, so it's going to go up like this. Now, here's the thing, is that if you calculate this is the angle, well, this isn't the point of impact with the x-axis, right? So the thing with this problem is you actually have to extend this line backwards so that it actually hits the x-axis here. And when you when you measure this thing against the x-axis, you end up getting 45 degrees. Now, if you look at each box, now if you look at the slope, right, the slope is 1. You didn't really even need this back end area to figure that out. If you look at this individual box right here, notice how a slope of 1 cuts it right in half. And each square has a degree of 90 degrees per corner, right? So if you bisect that angle, you should get an angle slope of 45 degrees. So what this chapter is trying to encompass to you guys is not only this notion of slope that we learned since integrated 1, but how slope actually creates an angle with the ground of elevation that it's sloping from. We will eventually learn this notion of how an angle here is connected to this opposite side of a slope triangle and this adjacent side of that same slope triangle, and we'll come up with a word that connects those three things together, this notion of angle, opposite, and adjacent. But that will happen in a later video. So for now, as always, leave questions and comments in the comments area, and I will see you all in the next episode.